There's recently been a lot of discourse about sparse autoencoders on social media, including a sparse autoencoder bubble. So in this video, I'm going to very briefly go over what sparse autoencoders are, some recent results that have happened, their applications to Vision, and finally, for the remaining part of the video, we will load an SAE with the Prisma library and examine an image and check out its latent features. If you want to jump straight into how to use the library, jump down to the timestamps below. Sparse autoencoders were originally proposed to deal with superposition, or when you examine a unit of your network, you might find it contains multiple features like cats or sheep and dogs all at once in a large jumble. So sparse autoencoders were proposed as a way to disentangle superposition to make the inner units of your neural net much more interpretable. A sparse autoencoder is trained on the activations of a given layer of a net. So for example, if I have the activations of layer 10, I train a sparse autoencoder to reconstruct those activations. And the sparse autoencoder has one hidden layer that's super wide. So it might be like 16 to 128 times wider than the original net. This is also called sparse dictionary learning. And now you're re-representing that information in an overcomplete basis, which means in theory that now you have disentangled your original units into units that are human interpretable. So instead of a single neuron containing a jumble of concepts, individual neurons may contain crisp concepts like separate neurons for horses, separate neuron for dogs, separate neuron for sheep. Due to jargon, the neurons of a sparse autoencoder are often called features. We can also call them SAE units or SAE latents. I personally liked SAE features because you could extract pretty interesting and precise latents from the network. For example, CLIP has this mustache feature, which is very specific, and also the mistakes that the mustache feature contains are pretty understandable, like the broom and the slug could be construed as a mustache. So I was fascinated initially by sparse autoencoders because it's a way to examine the model's ontology by re-representing its intermediate representations in a different way. There's recently been a lot of discourse as to, are sparse autoencoders useful, what are their limitations, and what are their first principles? The past year and a half has seen a bit of a social media bubble with sparse autoencoders, with some negative results that include a lack of common features between SAEs trained with different random seeds, features appearing in randomly initialized transformers, and a lack of usefulness in downstream applications. But they have been proposed as a useful tool in auditing the model for dangerous behaviors. Overall, as a research community, we're still fleshing out quite precisely what their limitations and first principles even are. This is partially just the way research goes. It reminds me a lot of the introduction of linear probes to examine intermediate representations in 2016 and subsequent work that really stress tested linear probes and really examined their limitations in terms of what they can tell us about the network. The last year and a half or so have really focused on SAEs in a hill climbing way, where it's like, oh, can we train better SAEs that have a better reconstruction loss or better sparsity reconstruction trade-off? But now the focus has really shifted from hill climbing to more rigorously understanding what we're even doing and what the limitations of that are. My favorite interpretation of SAEs are as analytic probes that tell you something about the representation. For example, you can use GEMMAscope SAEs as a snapshot of a language model. And this can be very useful, say, when examining a VLM, in which you have a vision encoder that is hooked to a language model and then fine-tuned end to end. Here, because the GEMMAscope SAEs were trained on language, you can learn pretty interesting stuff about VLMs and the distribution. Like, for example, vision tokens are a much higher density than language tokens, which in the case of a VLM might be inefficient. I'm very interested in laying out rigorously the first principles for vision, including whether they could be useful. SAEs and vision operate subtly differently from language in that you have specialized tokens like spatial tokens in your CLS token, and vision overall is a much denser data distribution. There has been pretty interesting work in Vision SAEs already, like universal SAE and archetypal SAE. All paper links are below. And these SAEs also deal with the problem that SAE features can be unstable, so both are proposing different inductive biases, but in different ways. I'm further interested in connecting past literature on autoencoders like beta VAE, which imposes a pretty strong inductive bias of disentanglement to get very orthogonal features. And there has been very little work connecting that to the present SAE stuff going on right now. There are also variants of SAEs rapidly coming out, like transcoders and crosscoders, which are in some ways more principled and more general. For the sake of this demo, we're just going to be focusing on vanilla SAEs because once you understand that, it's pretty easy to understand everything else. The Prisma library contains two parts. The first part is circuit code, very similar to Transformer Lens, where you can pretty easily cache intermediate activations to examine their representations for whatever interpretability purpose you may need. The second part is sparse autoencoder training and evaluation code, so you can easily train and evaluate sparse autoencoders for vision models. We've hooked vision encoders from Hugging Face and the open CLIP library, so it's pretty easy to load whatever you want. We're also releasing a suite of SAEs. We have CLIP, Dino, Top K, CLS only, spatial only, and a variety of interesting things to examine. In this demo, we're just going to keep it super simple and load a vanilla sparse autoencoder, feed in an image, and check out what features activate for that given image. So that said, let's get started. We're going to be working on a Jupyter notebook, so feel free to follow along or check out the finished version right below. And feel free to jump to the timestamp that's most relevant to you. For this demo, we're going to use Colab, which is super accessible, good old Colab. So let's start by creating a new notebook. And the first thing we're going to want to do is, well, I'm going to name this. The first thing we're going to want to do is change the runtime instance to GPU. And remember to do this, otherwise you're going to have to start over. So now that we have a GPU, we're going to clone the bleeding edge version of the Prisma library. So I'm just going to go to GitHub and I am going to snag this URL. And I'm just going to do a git clone. Okay, perfect. And as we're cloning in, we're now going to want to install it. Colab doesn't save state when it comes to terminal commands for some reason, so my cd and my pip install are on the same line. Okay, I'm gonna fast forward through the library install unless, you know, it's so riveting that you want to watch it. Excellent, it is now installed, so now we can move on and we can load our SAE. So let's start with doing that. There are a variety of pre-trained SAEs that we can choose from. If you go under our documentation, we have an SAE table full of SAEs for all sorts of layers. So for the purposes of this demo, I'm going to pick layer 10 MLP out. So it may come as no surprise that layer 10 is more interpretable than the layers before that, because by then the neural net ideally has separated the data into a way that is more human interpretable. But I also have the hot take that layer 10 is more interpretable than layer 11 for certain reasons having to do with the way the contrast of loss is optimized, but someone might want to check that with auto-interp scores instead of just taking my word for it. And we're going to look at MLP out SAE because I also suspect that's going to be more interpretable than the residual post, which contains information from the residual stream and past layers. Okay, so we're just going to grab this URL. And while we're here, let's just quickly look at the structure of this Hugging Face repo. So files and versions, we have two files. We have a config and we have a weights file. So the weights are the weights of our sparse autoencoder, and the config sets up our sparse autoencoder object. So let's go back and let's enter in that information. So we know that this is our repo ID. We know that our weights file is weights.json, no weights.point, and our config file is config.json. Perfect. Okay, so we have that. Now let's load the Hugging Face API so that we can actually snag these files. I love Gemini autocomplete. Perfect. All right, so this should load both our weights and our config. Downloading 302 million parameters. Seems good. Awesome. Okay, now we have those. So now let's load our sparse autoencoder object. So we're going to do SAE import sparse autoencoder. SAE equals sparse autoencoder. Nice try, Gemini, but not quite. Load from pre-trained, and we're just going to load the weights path. We don't have to worry about the config path because the config should have automatically downloaded it to the weights file. Whoops, forgot an S. No model named VIT Prisma. Okay, so there's something annoying about Colab where if you download a repo from git clone, you have to restart the runtime and run everything again. I don't know why, it's just one of those idiosyncrasies, and I probably should have mentioned it in the beginning, but no worries. I am going to restart and run all. It's not actually going to install it all over again. It's going to recognize it's there. And now it should be able to find our VIT Prisma repo. Perfect. We now have our SAE. So let's just check it out. Sparse autoencoder, perfect. Activation function ReLU, and it's hooked so we can grab activations from the latents, which is a super wide dictionary hidden layer, anytime. And the other thing we want to check out is the config. So if we do SAE.config, we notice that we get a lot of information about the SAE. And the most important thing here is the model name, and this is the exact model, the exact variant of CLIP that it was trained on. So this model was in particular trained on OpenClip, patch size 32, and we know exactly the version. It was trained on datacomp. And some of the other stuff here that might become important is that we're just confirming that this is on layer 10. We already knew that, but just in case we want to, that information is also stored in the SAE itself. And the layer subtype is hook MLP out. So we're getting the output of the MLP layer before it's added back to the residual stream. So cool, that's great and all. The next thing we have to do is actually load the model itself. And after that, we have to load a data set that we're going to use to evaluate our SAE features to see what they do. So let's start with loading the model. And loading the model here is loading a hooked model as you would in Transformer Lens. So here for the model name, we can just grab the SAE config model name instead of retyping it out. and we're going to do model equals load hooked model name. So this here is grabbing the correct data from OpenClip, the correct weights from OpenClip, and inserting it into the hooked model. Okay, so let's move our model to CUDA. And let's also check it out. So this model is a transformer, so it's almost exactly what you'd see in language, with a few subtle differences. So you have your patch embeddings up here, and you don't really have a dictionary. There are no dictionaries in Vision in the same sense there are in language, and as a result, there also are no on-embedding layers. You just have your output, and your output is just your tokens, but in the case of CLIP, the output that matters is your CLS token, which is what gets optimized in contrastive loss. And I'll go a little bit more into CLS tokens versus spatial tokens later. So now that we have loaded our model, our next step is to load our data set to evaluate the sparse autoencoder. So the way you evaluate a sparse autoencoder is that you feed in a giant data set, and for every hidden unit, you take the top 10 or top 20 examples that most activate that unit. And this comes with several implications. The larger and more diverse your data set is, the better interpretation you're going to get of that feature. So for example, if I were to feed in a data set that only consisted of dogs, then I might get tricked into thinking that every feature only encoded for dogs. So this is also why you want your validation set to be as large as possible, and ideally it matches the initial distribution that the model was trained on. So CLIP was trained on CLIP data, which is private. The closest open data is MetaClip data, which the links of which are open source. But because we're on a Colab and we're kind of limited in our GPU memory and just general memory, we are going to just use ImageNet validation, which is good enough for our purposes. But keep in mind that if we used a larger and more complex data set, our results might be a little bit different. So let's load ImageNet validation from Hugging Face. Okay, so here's the Hugging Face API. Let's see, and let's load ImageNet. Oops. While that's loading, let's load a transform so that we can transform the data into the correct normalization for CLIP. This is a pretty standard transform. It just does a normalization based off mean and standard deviation. Our data set is going to load. I actually don't know what format this is going to load in. I'm curious to find out because I'm curious how we're going to apply the transform. Maybe we need to write a quick data set class that applies the transform, but let's find out. Okay, so let's just check the type of the data set that we just loaded. And we can see that it is just what you'd expect, dataset dictionary. And what we want to do is create a wrapper class so we can apply the transform from the previous cell to our data set so it's appropriately normalized for the CLIP model. So I'm going to write an ImageNet wrapper, and let's see how much Gemini can anticipate. This is looking pretty good so far. This is close, but not quite. I want to return the label as well. Label, and also I want to transform the image to RGB. Perfect. Just because sometimes a black and white image sneaks in, and that's only one channel, and it causes an error. Okay, this is looking good to me. I now just want to load the data set and write a data loader. Okay, let's write a data loader. Okay, let's make the batch size 4 because Colab has like pretty limited GPU memory, and we're going to importantly set the shuffle as false. And the reason it's important to set the shuffle as false is because we're going to be retrieving the maximally activating indices of the relevant image. So if it's shuffled, we won't be able to retrieve them. Okay. Finally, we are going to visualize our data set just to make sure that we're all on the same page, which is just generally a good practice when you're dealing with a new data set. And because this is ImageNet and it's not shuffled, I expect that the first few entries to all be fish because class 0 is tench. So let's see if that holds up, and let's just write a quick function to visualize the image. Okay, let's see if Gemini knows what the mean and standard deviation is. Aha, that looks correct. And now let's import Torch Vision and import matplotlib, and let's write a visualization function that looks good. We don't need this convoluted code because we already loaded the images in the previous slide. And this looks great because they're all fish. Yay, nothing like a guy holding a fish. So great. Okay, let's now move on. So we've loaded our data set, we've loaded our base model, and we've loaded our sparse autoencoder. So we have these components that are necessary for the SAE evaluation. The only thing that we're missing is loading in the actual image. So we want to load an image, pass it through the model, pass it through the sparse autoencoder, and check out the sparse autoencoder's latents to see if any of them are interpretable or telling us about certain characteristics of the image. So the rest of this notebook will now have 2 parts. The first part is actually feeding in that image, and the second part is then noticing which features activate the most for that image, and then running an evaluation on those features by feeding in our entire ImageNet data set and noticing which images maximally activate the features of our choice. So for example, if we feed in our image, we notice that 10 features activate a lot for that image, we're going to take those 10 features, the 10 indices of the hidden layer of our sparse autoencoder, and we're going to feed in all 50,000 images of ImageNet validation, and we're going to return the top 20, top 10, top 20, top N images that maximally activate each of those 10 features, which gives us semantics for what those features actually represent. So let's get started. Let's find an image to load. So I'm gonna load an image here of parrots because I like parrots and they're colorful. And let's just do a wget. Parrots, JPEG, and then I put in the URL. Okay, so parrots are now saved to our Colab. And now let's just visualize the parrots just to make sure that they're loaded properly. We already loaded the transforms, but it's okay. We can load it again just so we are keeping track of what we're doing. Okay. Beautiful, we have our parrots. So this is the image we're going to be evaluating. We want to see what features of this image the model is picking up on. So let's now actually feed the image into the model. So forget about the sparse autoencoder for a second. We're just going to feed the image into the model, and we're going to cache the activations at layer 10 MLPL specifically. And we're going to feed the cached activations into our sparse autoencoder. So just so we're clear, there are two steps. Like step 1, feed image into model. Step, I guess 1.5, cache activations at layer 10 MLPL. And step 2, feed the cached activations into the SAE. And then step 3 will be see which SAE features maximally activate. Okay, so I'm gonna call this part 1. Part 1. And after that, we'll do part 2, which is what are these features? So part 1, which features activate the most? Which SAE features? What are these SAE features? And this is when we're going to feed the entirety of ImageNet validation, which is about 50K images, into the model and then SAE, and keep track of the images that maximally activate our chosen features from above. So in step 3 of above, we're going to keep track of, say, let's just keep track of 5 features. Top 5 maximally activating features, so just the features that spike the most by magnitude based off the image, and that's what we're going to look at. Okay, so let's get started. So let's do the first step. Let's feed the image into the model. And this code just works like transformer lens, so we can just do run with cache, image unsqueeze to CUDA. And so basically, we're going to also add a names filter just so we're caching our chosen layer. And we're not caching literally every single layer because that's a waste of memory. So let's run that. Okay, great. I'm just going to print out the cache just so we can see. Perfect. It's only cached the activations of block 10 MLPL. Perfect. So we did step 1. We did 1.5 as well. We can even say activations equals cache SAE config hook point just to extract those activations from the cache dictionary. And now we're going to feed our activations into our SAE. So we're going to do output, feature acts, and then a bunch of other data is going to come out of this, but that's not important for now. And SAE encode activations. Our output is going to be the reconstructed model activations. So we expect the dimensionality to be 768, while our feature activations are the super wide dictionary. So we expect that to be around 50,000 or so. I'm just gonna check the shape of the output and the feature acts. And that's exactly what I expect. So just so we're all on the same page, we have batch sizes 1. We have 50 patches. So the image has basically been patchified into 49 patches. Each patch is 32 by 32 pixels, and they're tiling the image in a way that does not overlap. And then we add at the beginning, we're prepending a CLS token, which has index 0, which is accumulating global information about the image. And the dimensionality of our model is 768, which is about the size of GPT-2 small. And our sparse autoencoder is also batch size 1, 50 patches, but our dimensionality is 64 times wider than that of the original model. So again, just so we're super clear, our CLS token, which is our global token, is index 0. So if we want to access the CLS token, which we will later, spoiler, this is how we do so. Okay, enough of that though. Let's see which SAE features maximally activate for our image. So we already have pre-built code that does that. You can do it manually, but just for the demo or just to save some time, we have some code that gets this for you. And you can go check it out if you're curious. This code is extremely simple. It just looks at all 50,000 activations for that SAE, and it just returns like the top 10. That's it. You could write it yourself in 2 seconds. And so I'm going to do top indices. Okay, yeah, let's do top 5. Whoops, and top. Oh, right. This is important. So I fed in all 50 patches, which is a mistake because now the function is confused. It doesn't know which of the 50 patches to look at. So we need to make some choices here. We need to either pick the CLS token, or we can take an average of all tokens, or we can take an average of all spatial tokens, which are the non-CLS tokens. And all of these are going to lead to slightly different features. If I'm to take the CLS token, I'm more likely to get global representation, which is fine for later layers, but this might be incoherent in the earlier layers. I can take the average of all patches, and then I'm more likely to get diffuse features. And finally, I could just take the maximum patch value. And if I do this, I'm more likely to get pointy or concentrated features like characters or words. It's not entirely clear what the best practices are yet, but the safest bet here is to just look at the CLS token, especially because we're in layer 10, so it would have already formed. So I'm going to do what I did earlier, and I'm going to do feature ax CLS, and I'm going to just grab the CLS token. And the final reason this is not working is because I need to squeeze. I need to get rid of the final batch. And now it should work. Perfect. Okay, so we can see that these outlier features activated the most for this image. And that's great. But I don't know what these features are. Like, I don't know what this means. So it's good now to actually examine these features and see what semantics they contain. And the way we do that is through this maximum exemplar method, where we're feeding in 50,000 images and we're seeing which of the 50,000 images most trigger these 5 features. So let's jump into doing that. The next section of this demo is going to have kind of elite codey vibes because we are just coding a function to cache the top 20 images for each of these 5 features, and then we're going to visualize them. So if you're feeling super lazy, you can easily feed this problem into ChatGPT or Claude or your favorite LLM, and it'll solve it for you. But that's not a good use of exercising one's mind. So we're going to code it ourselves. And it's going to be a little bit leak codey, but that's the thrill of it. Okay, so let's first start by writing pseudocode of what we want to do, and then we can go and flesh out that pseudocode. So I want data structure that captures top n values of given features and corresponding image indices of those values so we can retrieve those images later. One thing that I really quickly want to say, I mentioned this earlier, but it's really important to reiterate that the size and diversity of your data set does depend on the semantics you're going to get returned. And ideally, of course, we want our validation set to approximate what the model was trained on. So ideally, we would be doing this with MetaClip. But MetaClip is huge and not really viable for our GPU and in our Colab contexts. So we're just using ImageNet validation. But keep in mind that the features will look more and more crisp and potentially different depending on whatever data set you're evaluating it with. So let's do that. We have that data structure capturing the top n values, and then we're going to iterate through data set, and then we're going to cache the values for every feature. So like iterate through dataset. I guess we have a nested for loop, iterate through features, and then we're going to iterate through the images in a given batch and compare to the initial, to the running list. Okay, so let's first set up our data structure. Okay, I want more, I think, of a dictionary values. And here, I want to just do top 20, but you can change this. Dataset indices. Okay, and this will be the corresponding top 20 images for those values. So this will also be 20. Okay. Now let's iterate through a data set. So for batch, index, image label, enumerate file order. Let's send our batches to CUDA, batch labels to CUDA. Let's keep track of the batch size because we need a global indexing scheme so we can retrieve our images later. Okay. This is all looking good. Yes, we do want to feed it into the model. We do want to put the names filter, so we're only caching that layer so we don't blow up our memory. And this is all looking good. This is exactly what we did earlier. Now we want to feed it through our SAE. Perfect. We don't need encode. We can just do activations. We want to grab the CLS token. Perfect. We also just want to grab, oh no, we're going to iterate through every batch. Okay. So that's looking good. And keep in mind that we don't care about every feature. We don't have time to check the semantics of all 50,000 features. We're only going to check the semantics of these top 5 features that we see above. So I'm going to make this top indices. So the dimensionality of this should be, it should be like 5. And now we want to iterate through our tensor of 5. And for each feature, we want to check every image in the batch and see if we should add it to our list or not. So let's start. Okay, Colab is getting ahead of me. It's not quite what I want to do. So I'm iterating through the features in the top indices. So here are the 5 features I'm iterating through. And now I want to get their values. CLS. We don't need this on the GPU, so we can detach it. I get the dataset indices. These are not dataset indices, these are batch labels. Silly Gemini. I am going to just get a list. And I'm going to create a start index here just to keep track of a global indexing scheme so we can retrieve these images later. And the batch size here should increment things properly. So here are batch specific indices. These are global indices to retrieve the images of the non-shuffled data set later. Okay. And now we want to iterate through the batch and compare every image to what is already in our list. Okay, perfect. So we have our current, this is not quite what I want to do. Gemini getting ahead of me with code that's not correct. I want to keep track of current values. Perfect. Current values and current indices. So I'm taking the current values and current indices of the batch, And now if my list is less than 20, I'm just gonna make this top K. I'm gonna make this a hyperparameter and I'll set top K up here. But you can change this to 5 or 10 or whatever, depending on how many images you want to cache per feature. So if our list doesn't have 20 yet, it'll add it to the list. But otherwise, let's get a minimum value. The minimum of the current value. So we'll take the smallest, and if a value is greater than the minimum value, we will then update the list. Okay, this looks great. So this is how we're keeping a running list of the top activations and their corresponding feature indices. It's not perfect. There is one flaw to this, and maybe you can point it out, but it's good enough for our tutorial purposes. So this is looking pretty good. Final thing I want to do is I want to increment the start index by batch size as we go. And this should keep track of the global indices in the data set, and we'll see why that'll be important later. And now I just want to run it. Oh no, tensor object has no attribute convert. Oh, okay, I see. Let's clean that up. Yeah, because it's already a tensor. This line needs to go here. Okay, now we should be good to go. Current value not defined. Oh, current values. Okay, it's loading. In the future, I'd recommend actually wrapping this in a TQDM just so we know how long it's going to take. But because it's iterating through 50,000 images, this can actually take a while. It's going to take us here probably about 15 minutes or so. So I'm going to, in a moment, cut the video and rejoin once it's done. I will say, though, that if you want to do like a really epic evaluation of CLIP, say you use ImageNet 21,000, that's 14 million images, it might take like 7 hours to run the entire data set through. And that's just part of the processing time if you're doing the most thorough evaluation that you can. Okay, so our code has run and we've collected the top 20 images for each of the 5 features. So now we just have to write a brief visualizer to see what those features are. If you're feeling lazy, you can just copy and paste all this code into ChatGPT and ask it to write a visualizer for you. But I'm just going to write one myself, the old-fashioned way, just so we can see what it's actually doing. I want to sort the dictionary that we had earlier. I want to iterate through the features. I'm going to grab the activation values and the activation indices. I'm going to create a plot grid. Let's see, it's square root of the image indices because we want 4 by 4 or Let's try 8 by 8. Okay, so now let's iterate through the indices and the activation values. I have to convert the image tensor back into NumPy. And we should undo the normalization again. Perfect. Okay. Okay, let's see if this works. I just kind of scrappily wrote it. I feel like there are probably some kind of bugs here, but let's see. I'm gonna do plot imshow. Why is nothing appearing? Interesting. Name sort is not defined. Sorted. All right, now let's try it. ImageNet indices is not defined. Should be feature indices. No, it should be activation indices. And this should also be activation indices. Unsupported type list and int. Right. So I turn things into a list up here, and I probably shouldn't. Let's try it now. No. Really? At what point do I just feed this into ChatGPT and ask? Let's do that. Okay. ChatGPT is giving me a modified version of the function. Let's see if this works. It worked. Yay. Oh, okay. And nice. So for our top feature, which is feature 3059, and we can go back here. Actually, this is not our top feature. This is one feature. But we can see that it is largely these parrots and birds, which intuitively makes sense given that the original image was largely parrots. So that is all well and good. And the next feature we're getting are all of these little cute birds that you would see in your backyard with bird feeders, which is a different feature than the first one, but it's still pretty connected to the original image. Our next feature are monkeys and trees. So maybe it's picking up on the leaves in the background. A more sophisticated version of this code would do heat maps, potentially, or feed in all patches and then do heat maps, because you can't do a heat map with CLS. But maybe, I don't know, that one's a little bit more of a stretch. There aren't really leaves in the photo, so I'm not really sure. But this is one of those features where it could be frequencies or something that isn't as human detectable, but is very much in the image. And the final one is planes, and this one makes no sense to me unless you want to try to stretch some analogy of flying. And the next one also doesn't really make sense to me. So you'll find that a lot of your SAE features don't seem directly applicable. It doesn't mean they're not. It could be edges or corners or shadows or things that we don't necessarily have language for that are prominent in the image. It could be that this feature activates for every image, so you may want to normalize the top features returned across a larger set of images instead of just the parrot. But that's all for a more sophisticated analysis. If I were doing a more sophisticated analysis, I would feed all the ImageNet validation images into the SAE, and I would categorize the features by how often they activate. So if they activate very often, these features might actually be junk because, well, junk in the sense they're not necessarily human interpretable. And maybe they need to be pruned out. So there is some literature on how to do this, but it's kind of out of scope of this video. I thought I'd keep this video kind of short and sweet, and I will see you guys next time. Everything is linked below. Feel free to check out the library and let me know what you think.